Welcome to this next video in the playlist on vector spaces. In this video, what we're going to do is state and prove the dimension formula, which is a formula concerning linear transformations. Okay, so firstly I'll just recap what a linear transformation is, what the image and kernel of a linear transformation are, and then we will state the dimension formula and prove it. Okay, so a linear transformation then is a map between two vector spaces which are both over the same field. So we're going to have a vector space capital V, which will be our domain vector space, and it will be mapped onto a vector space capital W, which will be our codomain vector space, and both of these vector spaces, V and W, will be over the same field, so over some abstract field capital F. Okay, now in order to qualify as a linear transformation, a map from the vector space V to the vector space capital W has to obey some nice properties, okay, specifically two nice properties. Okay, and these two nice properties are that T of V1 plus V2 has to equal T of V1 plus T of V2 for all V1 and V2 that you can possibly pick from the vector space capital V. Okay, so this is property number one here, and what this is saying is that if you take any two vectors you like from the domain vector space capital V over here, and you add those two together in the domain vector space, so V1 plus V2 in the domain vector space, and you then ask what is this addition of these two vectors mapped onto in the codomain vector space, the answer has to be the same as if you firstly map V1 into what it is in the codomain vector space capital W, and you map V2 onto what it is in the codomain vector space capital W, and then add the two of them together in the codomain vector space. Okay, and remember, this means that if you relabel up the addition law of the domain vector space according to this map T, then all of the composition table that you'll get, the relabeled composition table, all of the compositions in that have the same answer as they would have in the composition table on W, is basically what that's saying. Okay, then property number two concerns scalar multiplication and basically says the same thing. So you pick any scalar from the field, pick any vector from the domain vector space capital V, and it must be the case that T of C times V is equal to C times T of V. Okay, now, the multiplication here, the scalar multiplication that's in there, is scalar multiplication in the domain vector space capital V, whilst the scalar multiplication that's here is the scalar multiplication in the codomain vector space capital W. Okay, and this needs to hold true for all C is an element of the field capital F, and for all the V is an element of the vector space capital V, the domain vector space. Okay, so these are the two criteria then that a mapping must obey in order to be a linear transformation. And remember, this one effectively means that if you relabel up the scalar multiplication law on the domain vector space capital V according to the mapping T, then the composition table that you'll end up with, all of the compositions in that are the same as, well, the answers are the same as they would be in the scalar multiplication table on W. Okay, that's what this says. So, there's a reminder of what a linear transformation is. It's a very special function from one vector space capital V to another vector space capital W, where these two vector spaces are over the same field. Okay, the two vector spaces must be over the same field for this to work. Okay, so now what I want to do is just remind you of the definition of the kernel of a linear transformation and the image of a linear transformation, and we discuss all of this in much more detail than I'm going to do now in the previous video in this playlist on linear transformations, but we do need to just recap them because they are going to be very important in the dimension formula. Okay, so firstly let's start off with the image of a linear transformation, denoted ImT. Okay, so the image of a linear transformation is defined to be a subset of the codomain vector space, and it's defined to be the subset that contains all the elements little w of our codomain vector space capital W, such that little w has some little v in the domain vector space which is mapped onto it by the linear transformation T. Okay, for some v is an element of capital V. Okay, so it's all the elements in the codomain vector space here which actually have elements in the domain vector space being mapped onto them. Okay, so that's a very intuitive definition. It's the same definition as we would have in set theory. Okay, so the image of this function is just all of the elements of the codomain which actually have elements in the domain being mapped onto them. Okay, now what we show in the video on linear transformations is that the image of T is actually a very special subset of the codomain vector space. Indeed, it actually obeys the axioms of a subspace. So with the inherited addition and scalar multiplication laws on it from the larger vector space capital W, it does actually obey the axioms of a vector space in its own right. Okay, so the image of T is a subspace of the codomain vector space. Now let's go over the definition of the kernel of a linear transformation, denoted ker-T. Okay, so the kernel of the linear transformation is going to be a subset of the domain vector space, whereas obviously the image was a subset of the codomain vector space. Okay, and it's going to be all elements in the domain vector space which are mapped onto the zero vector in the codomain vector space. Okay, so it's all little v is an element of capital V, all elements of the domain vector space, such that if you look at what the mapping T maps little v onto, T of little v is going to be the zero vector in the codomain vector space. And I'll just underline that zero in red to denote the fact that that's the zero vector in the codomain vector space. Okay, so it's all elements of the domain vector space which are going to be mapped onto this additive identity in the codomain vector space, the zero vector. Okay, so that's the definition of the kernel of a linear transformation. And again, in the video on linear transformations, we prove that the kernel of a linear transformation is actually a very special subset of the domain vector space. It also is a subspace of the domain vector space. Okay, so there's the recap from the video on linear transformations. Let's now see what the dimension formula says. Okay, so the dimension formula is all about linear transformations. So we're going to have a linear transformation from a vector space capital V to a vector space capital W. Okay, and both of these vector spaces will be over the same field, but now the assumption I'm going to make is that this vector space capital V here, I'm going to make the assumption that that is finite dimensional. So the dimension formula only makes sense if the domain vector space here is finite dimensional. Okay, it doesn't work at all. It doesn't even make sense if the domain vector space is infinite dimensional. Okay, so now the statement then of the dimension formula. So the dimension formula says that the dimension of the domain vector space, dim V, okay, and that's why we need it to be finite dimensional, because we need this to be some finite value, is equal to the dimension of the kernel of the linear transformation. So remember, the kernel of the linear transformation is a subspace of the domain vector space. So it means something to say the dimension of the kernel of the linear transformation, because this is a vector space in its own right. So we can ask, what is the dimension of the kernel of the linear transformation? And I'll just underline that in turquoise here. Okay, plus, okay, so it's not complete yet, so we have to add on to this the dimension, and you might like to guess what I'm about to write, the dimension of the image of the linear transformation. So again, the image of the linear transformation is a subspace of our codomain vector space capital W, so it will have a dimension as well. Okay, my assertion here, the assertion of the dimension formula, is that the dimension of the domain vector space is going to equal the dimension of the kernel of the linear transformation plus the dimension of the image of the linear transformation. Okay, and the rest of this video is going to be devoted to understanding why it is that this formula is true. Now, really, the dimension formula, the actual formula here itself, is not as important as the understanding of why it is true. Okay, so really this formula just captures in a nice line a very important concept. Okay, so when we're proving this, we will understand, we'll get a very good understanding of linear transformations. Okay, so really, the actual formula is not as important as the lesson that you learn by proving this. This just captures in a nice line the lesson that you learn in proving this. Okay, so the proof is more important than this actual fact here. Okay, so let's try and understand then how we can prove this formula here. So the way that we're going to prove this formula is we're going to try and produce a basis of the vector space capital V. And the way that we're going to do this is we're going to start off with a basis of the kernel of the linear transformation and extend that up to a basis of the entire vector space capital V, the domain vector space. And then what we're going to consider is if we write all vectors of this vector space as linear transformations of those basis vectors of that basis that we've just constructed, can we gain some insight into the dimension of the image of the linear transformation? And we are going to get this basically. So for a while, just go with it and you will understand where this is going to go. It's not too difficult at all to prove this, it's very easy actually. Okay, so what I'm going to do then is I'm going to find a basis for my finite dimensional vector space capital V. So we know that when we have a finite dimensional vector space, it's very nice, we can always find a basis. So what we're going to do is we're going to start by finding a basis of the kernel of the linear transformation. Now remember, the kernel of the linear transformation is a subspace of our finite dimensional vector space capital V. And we know from our study of finite dimensional vector spaces that any subspace of a finite dimensional vector space is also finite dimensional. So we're going to be able to find a basis of the kernel of T. Okay. Oh, and just before we go on to the proof of this actually, I'd like to give you a bit more terminology. So come back just to the formula, because I'm going to give you a bit more terminology before we go any further. So the dimension of the kernel of T and the dimension of the image of T, these have other names, okay, which you will hear because they're still in common use. So the dimension of the kernel of a linear transformation, this is often called the nullity of T. Okay, so this is often called the nullity of the linear transformation, and it's often denoted just by little k. Okay, and that's the bit that prompted me to think of this, because we're going to suddenly use this little k, and I haven't actually defined it yet. Okay, so the dimension of the kernel of a linear transformation is often called the nullity of the linear transformation. So the nullity of a linear transformation is just a number associated with that linear transformation. In addition, the dimension of the image of a linear transformation, that has a fancy name as well. That is often called the rank of a linear transformation, or the rank of T, and that's denoted usually by a little r, like so. And for this reason, this dimension formula is sometimes also called the rank nullity theorem, but we'll call it the dimension formula. Okay, so just a few bits of notation there. So we're going to have this constant little k, which is just the dimension of the kernel of T, or the nullity of T, and we're going to have this constant little r, which is the dimension of the image of T, also called the rank of T. So that's just words, that's just names. Okay, back to the actual proof. So, the kernel of T then, this is a finite dimensional vector space if V is a finite dimensional vector space. So what I'm going to do is create a basis for the kernel of T. Okay, now how many vectors are there going to be in the basis for the kernel of T? Well, that's going to be the dimension of the kernel of T, which we now are denoting little k. Okay, so I'm going to write out my basis for the kernel of T here then. So I'll have a vector v1, v2, all the way up to vk, and it will be sensible probably to draw a picture for this. So we'll have our vector space capital V here, okay, and I've got the kernel of my linear transformation here as a subspace of my vector space capital V. Okay, so I'll colour this in orange here, and now what I've done is formed a basis of the kernel of T. So this is a set of vectors from the kernel of T, so all of these k vectors are in there, and they span the entire subspace, and they're also linearly independent. Okay, so here's my basis of the kernel of T. Now, what I want to do is extend this basis of the kernel of T so that I can make a basis of the entire vector space. Okay, and you can always do this because if these vectors are linearly independent in the kernel of T, the subspace of the vector space capital V, they're also going to be linearly independent in the entire vector space capital V. Okay, so this is going to be a set of linearly independent vectors in the larger vector space capital V. After all, they are all vectors of capital V, and to be linearly independent, all it means is that there has to be only one linear combination of them that gives the zero vector, and that has to be the trivial linear combination where all the coefficients are equal to 0 in the field. Okay, so if that's true in the kernel of T, this subspace, then of course it's still going to be true in the larger vector space capital V. So this is a set of linearly independent vectors in the vector space capital V. Now, of course, if the kernel of T is not equal to the entire vector space capital V, then the span of this will not equal the entire vector space, so we're going to have to extend it up to form a basis for the entire vector space. But we know that we can always do that from our study of finite dimensional vector spaces. If you have a set of linearly independent vectors, what you can do is add a vector that is outside of the span of these, and that set will still be linearly independent, and then you can just continue on until you've got enough vectors to span the entire vector space, and that will then be a basis for our entire vector space. Okay, so what we're going to do then is we're going to add in vectors from the portion of the domain vector space outside of the kernel of the linear transformation to extend this basis of the kernel of the linear transformation to a basis of the entire vector space. Okay, now I'm also going to give you one other little piece of notation. I'm going to denote the dimension of V as little n. Okay, that will just be easier to write than the dimension of V. So just another piece of notation there for the dimension of the entire domain vector space here. So we'll have V1, V2, all the way up to Vk. Okay, so those are all the vectors from the kernel of T, and now what we're doing is adding in more vectors, so we'll have Vk plus 1 all the way up to Vn, so that we have enough vectors that this basis now has the number of vectors equal to the dimension of V, which we know all bases must have. Okay, so there we go. We now have our basis of the entire vector space V. So all I've done so far is start off with a basis of the kernel of T and said that I can extend that to a basis of the entire vector space capital V. Okay, and if you're not comfortable with the understanding of why that is true, watch my videos on finite dimensional vector spaces. We go through all of this and prove that any linearly independent set can be extended to a basis. Okay, so we've now got a basis then of our vector space capital V, and we're going to use this to gain a lot of insight into our linear transformations. I'm going to add a bit more onto my picture here now. So I'm going to have the vector space capital W now shown here, our codomain vector space. I'll also have the linear transformation actually shown there. I also might add on to here the image of the linear transformation, which we know is a subspace of our codomain vector space capital W over here. Okay, so how then are we going to use this basis to gain an understanding of our linear transformation capital T? Well, the reason that we can gain understanding through this is that we can express all of the vectors in capital V as linear combinations of these n basis vectors. Okay, so that's just the property of a basis, but then we know that linear transformations interact with bases very beautifully. Okay, and as soon as we know where the linear transformation sends the basis vectors, we know where it sends all vectors, and that's going to actually be very powerful. Okay, so if we've got some arbitrary vector then in our vector space capital V, it's going to have the form C1 times V1 plus C2 times V2 plus all the way up to ck times vk, and then we're going to go on further, so we'll have plus ck plus 1 times vk plus 1 plus all the way up to cn times vn. So just a great big linear combination of all of the vectors in the basis here. Okay, so any vector in my domain vector space capital V can be written as a linear combination of the basis vectors like so. Okay, now let's think then what t is going to map this arbitrary vector from my domain vector space onto in the codomain. Okay, so what will t of v be equal to? Well, I'm just applying t to this entire linear combination here, and I know that when I apply t to a linear combination like this, something very beautiful happens, because what I can do is firstly split this down into t of all of the separate portions added together, and then I can factor out the scalars. Okay, so what this actually becomes is c1 times t of v1 plus c2 times t of v2 plus all the way up to ck times t of vk, plus then we'll have c of k plus 1 t of vk plus 1, plus, and we'll go all the way finally up to, and do I dare try and squeeze it in there? I will try, cn times t of vn, like so. Okay, so I've just got all of these basis vectors being mapped onto what they are mapped onto in the codomain vector space by the linear transformation t, and then the coefficients, the scalar coefficients, are unchanged there, just sitting in front of those. And the reason I can do that is I've just put t, I've just taken t of this, and then I've just applied the beautiful properties of a linear transformation. I've applied the addition one. Okay, and we saw in the video on linear transformations that when we have that t of two things added together can be split up in this way, it can be extended to an arbitrary string of things added together. Okay, so I've split this firstly up into t of this plus etc., and then all we've done is pulled the scalars out using the second property of a linear transformation here. Okay, so indeed t of an arbitrary vector in the domain vector space is going to have this form. All I need to know is where the basis vectors are going to go, and then we're in business. You can instantly then say where all other vectors in the domain vector space are going to be sent. Now, why is this very interesting? Well, the added interest is that I chose this basis very carefully. I chose it so that I was extending a basis of the kernel of t to become a basis of the entire vector space. Okay, this is true for any basis. What's suddenly really interesting about using this basis is that I know that t of v1, t of v2, all the way up to t of vk are all equal to the 0 vector in the codomain vector space. And the reason is, these are all vectors for the basis of the kernel of t, so all of them are in the kernel of t. Okay, the vectors of a basis of a vector space are in that vector space itself, so all of these are in the kernel of t, and therefore the linear transformation sends them onto the 0 vector. Okay, so this is the 0 vector in the codomain vector space, this is the 0 vector in the codomain vector space, and this is the 0 vector in the codomain vector space. Okay, so we've got 0 in all of these positions, and when you scalar multiply the 0 vector by any element of the field, you'll always just get the 0 vector back again. So that means this entire thing will be the 0 vector, this entire thing will be the 0 vector, etc., all the way up to this thing being the 0 vector. So we've just got k lots of the 0 vector added together. So effectively, it's just as though this entire bit here doesn't exist. Okay, so we can just omit that bit entirely. So t of v just becomes what's left over here. All I need to know is where do the basis vectors that are outside of the kernel of the linear transformation, where do they actually go? Okay, and then my vector will just be mapped onto what's left of the linear combination involving those, well, where those basis vectors have been sent. Okay, so that shows us that t of v is something of this form: ck plus 1 t vk plus 1, okay, plus all the way up to cn times tvn. Okay, so all that matters is where those basis vectors that were outside of the kernel of t are actually going to be sent to by the linear transformation. And I've now shown that any vector in my vector space is going to be sent onto a linear combination of those. Okay, so this will then be my next claim. Okay, and we'll prove this in the next video. What I want to try and prove next is that if we put into a set these vectors t vk plus 1, and then we'll have t vk plus 2, all the way up to t vn, i.e. where all of the basis vectors that are outside of the kernel of t are sent to, I claim that this is going to be a basis of my codomain vector space, capital W. Okay, and I claim that if I can show that this is a basis of my codomain vector space, or rather, wait a second, sorry, not a basis for the codomain vector space, a basis for the image of the linear transformation, because it's not necessary that we're being mapped onto the entire codomain vector space. Okay, so I claim that this is a basis for the image of the linear transformation. Okay, and if that was the case, then how many vectors would there be in this? Well, there would be n minus k vectors in this. Okay, so because there are n vectors in the initial basis of the domain vector space, we've subtracted off k of those, so there's n minus k left. Okay, and that then would be the dimension of the image of the linear transformation, i.e. the rank of the linear transformation. Now if we add that to k, the dimension of the kernel of the linear transformation, of course we'll get n back again, the dimension of the domain vector space. So all that's left to prove is that this is in fact a basis of the image of the linear transformation. Okay, and we'll do that in the next video.